Today we're going to discuss topology, specifically how topology is implemented in the geodatabase through ArcGIS. We'll also have a general discussion of topology and talk about another type of topology, map topology, that is available through a basic license of ArcGIS. A lot of what we'll talk about will be geodatabase topology because we are in the geodatabase portion of our course. But we need a little bit of background to help us understand where we are with topology and why we are where we are and what the history of topology is. So the term topology in the context of GIS essentially means the spatial relationship between features. So topology is the mechanism used in a GIS to manage how features are related to each other. It's actually a branch of mathematics. It's a part of geometry, so the geometric properties and spatial relations that are unaffected by continuous change of shape or size of features is one definition of topology. It's planar geometry. You'll see topology referenced in other technologies like network topologies for a network administrator to model how networks are connected with servers and computers and routers. But again, in the context of GIS, when you hear the term topology, you should think about how features relate to each other. So in general, these kind of topological relationships, and you'll also often hear them referred to as spatial relationships. The ones that are kind of a basis for what we do are adjacency, which defines which vector features are next to each other, connectivity, which arcs connect to each other, containment, which vector features are within other polygons, and coincidence, which vector features occupy the same space. So you'll see these basic types of spatial relationships expanded on in many different topology rules that are available through geodatabase topology. So topology is important for a couple of big reasons that we'll get to soon. So historically, topology was part of the actual data structure, and what this means is it was part of the actual data format. And so another historical look back at the ArcInfo coverage, that data model we talked about early on, it was the first topological data structure. Topology was actually stored in tables. If you remember looking back, we had from nodes and to nodes that gave lines connectivity and direction. We also had right polygons and left polygons on each sides of the arcs. So this allowed us to look up how features were connected and the relationship, the spatial relationship between them. It allowed us to look it up in a table. A big thing about topology back then was that it was based on a shared geometry model where two adjacent polygons that had a line in between them, that line was only stored in the database one time. It was done this way on purpose to save space from storing a line as part of the definition of each polygon, where you'd have two lines on top of each other, essentially identical lines. That term is coincident. So that's the old way of doing things, and we'll see a table of the ArcInfo coverage and look at how it was actually stored in the table. Today, the geodatabase stores topology as feature, behaviors, and rules. So I won't read this whole slide to you, but it's a different kind of approach for modeling geography that uses a set of rules, and it uses the computer's ability to calculate coincident vertices and features on the fly to determine spatial relationships on the fly in the memory of the computer without explicitly storing all of that information in a table. So that's how it's done these days. It's more flexible, it's more powerful, it allows the topology to be defined by the user rather than in the data structure, and it's really a function of how computers have changed over time. So when the ArcInfo coverage was the predominant data format, computers did not have large amounts of RAM or random access memory, and the processors were not as fast as they were today. They had relatively smaller hard drives, so things were not done in the memory of the computer on the fly, as you'll hear the term expressed in this PowerPoint. Back then, you would commonly go read from a table on your hard drive, read from disk, information from a table, and extract the information you need. Today, computers are very different. They are very powerful with more powerful processors, multi-core processors. Many computers have many gigabytes of RAM now. And so things can happen on the fly in the memory of the computer. Today, the last thing you want to do as far as the speed of a computer goes is go read from your disk. You want things to be happening in RAM and in real time or on the fly, and that's how things more commonly happen in today's computer technologies. So why in the world do we need topology? We need topology for a couple of big reasons. It provides the basis for spatial analysis. So with the GIS, we're often want to know what feature is next to another feature, or what roads connect to a different road. So topology helps us determine simple types of spatial analyses like the area and length calculation of features, as well as doing something like a select by location in the software. Say, select all the birds' nests that are in this particular type of forest. And so those are simple types of spatial analysis that are made possible through topological behaviors in the data and in the software. And then of course there are more complex types of analysis that are made possible by topology, things like tracing flow through a utility network or routing a bus through a transportation network. These require connectivity of arcs through nodes, and if that connectivity is not built in and there's not a system of topology to help keep up with how features are connected, you can't route a bus through a network of lines and arcs. So topology is required for spatial analysis. It's also very useful for ensuring that features are spatially correct, or sometimes you'll see that it's used to ensure the integrity of data. So the topology allows you, while you're editing, to ensure that polygons don't overlap, or there's not gaps between parcels, or maybe bus routes follow a road or are coincident with a road, or maybe roads connect at intersections. So topology allows us to spatially analyze our data, as well as ensure the integrity of our data in being spatially correct. So okay, so here's a couple examples of tables, and this is really to point out the ArcInfo coverage info table. If you remember, the ArcInfo coverage used an info database system. The database was called info, and that's where it stored its attributes as well as its system defined fields. And so if you remember, there was an area and a perimeter field on polygon feature classes in a coverage. There were also these pound and ID fields that kept up with IDs for tracking the features in the layer. So the perimeter and the area is something that was automatically generated, or that was generated when you issued a command called build or clean on the coverage. There were also tables that kept up with the from nodes and the to nodes and the left polys and the right polys. So when you wanted to find out what polygon was to the right of a line, it went and looked it up in this table. These days, with the geodatabase, the tabular information is stored in a relational database management system table, and you have a shape length and a shape area field on polygon feature classes that keep up with area and perimeter, respectively. If it was a line feature class, the shape length field would keep up with length. So, what about shapefiles? What's in a shapefile table similar to these? Remember that shapefiles are a non-topological data format. They don't store area or perimeter. They also don't store from nodes and to nodes. You are able to calculate coincident vertices on the fly using the software, the application layer on top of the shapefile, but it's not part of the actual data structure or data format. So when we talk about topology, we're talking about vector data. Okay, so in the Esri world, we have coverages, shapefiles, and geodatabases. And when we talk about modeling topology, we're always talking about doing that on vector-based systems. So, more review. Remember the topological data structure of the ArcInfo coverage. This had stored topology. These relationships were explicitly stored in the tables. The relationships were generated using clean and build commands. Lines were simple. Shared polygon boundaries were only stored once. There were some advantages to this. A big advantage was it was really the only topological data structure back then. So it provided a way to handle digitizing and editing errors and artifacts. We would digitize data back in the ArcInfo coverage days, and after you digitized, you would run a command that showed you anywhere your features were not connected, and then you could go back in and update those. So running the build and clean commands would tell you where things were not connected, and you were able to fix those non-connected parts and then reissue the command, and it would build the tables that showed the from nodes and the to nodes and the right polys and the left polys. So it really helped with automating how we handled digitizing and editing errors. It also enabled spatial analysis abilities like determining adjacency, connectivity, and containment. Again, it was the only data format back then that provided a topological data structure. So topological data structures back in the days of the coverage worked this way because they were developed when computer processing speeds were slow and hard drive space was fast. Lines and points were stored only once to save space, even though the hard drives were small. And the spatial relationships and spatial integrity of the data was checked by reading from the tables of topological information and returning an answer. Again, today, you try not to read from disk. That's called reading from disk. So I'll let you read through this slide, but it essentially shows how this line here, or arc, between polygons 2 and 3 here, this line stored one time in the table. And it shows the connectivity here, lines connected by arcs connected by nodes, areas defined by closed sets of arcs, and contiguity defined by shared arcs between two polygon boundaries. So just as a summary, remember that in the days of topological typical data structures where we had stored topology, it was implemented in a GIS to provide rigorous, automated method to clean up data entry errors and to verify your data integrity. The typical digitizing procedure back then was to digitize all the lines, to build the topology, label polygons, clean up slivers, undershoots, and then build the topology again, repeating the clean and build process as many times as necessary until you'd fixed any digitizing errors. So how about the shapefile? So we first had the coverage, and then came along the shapefile, and after that the geodatabase. So the shapefile was we refer to it as a cartographic data structure. It stores geometries of features, and points can coincide. Another advantage of the shapefile was that lines could be complex. They could have unconnected multi-part lines or polygons, similar to Hawaii. The difference in how the data was actually modeled and stored in the data structure was that this data format was based on a coincident geometry model, where the line between two polygons was stored in the database twice. It was part of the definition of polygon A on the left and part of the definition of polygon B on the right. So the two lines in between those polygons were considered coincident. They were considered identical in the software. The term identical, they're not really identical. For features to be considered coincident, or essentially the same, they must be within what's called a cluster tolerance. So we'll talk more about the cluster tolerance as we move through this PowerPoint, but just remember the term cluster tolerance. Any features within the cluster tolerance are considered to be coincident. So what in the world was the advantage of shapefiles? They weren't topological, but they were a simple structure that drew a lot faster than coverages. You could easily copy them from one system to another, whereas ArcInfo coverages were very difficult to copy from one system to another because of the way the info folder was built and the workspace was generated around multiple coverages in a workspace. The shapefile also has been adopted by almost all softwares as a common data exchange format, and almost all software packages support it now. So with the shapefile, with this cartographic data structure of the shapefile, we were given new ways that we could edit the data. Okay, so editing was approached from a feature-centric perspective and enforced planar topology when the feature boundary was digitized and labeled. So a lot of errors were eliminated by the feature-centric editing environment. What that means is much better snapping tools, and also tools within the interface, editing tools that allowed you to build polygons, allowed you to create adjacent polygons, tools that helped you to build topologically correct data while you were editing, instead of having to check for all that stuff after. In the ArcInfo days, when we were working with the coverage, the editing tools were very rudimentary. There was no tool for building a polygon. You had to build a closed set of arcs and then generate a polygon using the build and clean commands. So with the shapefile, there were also a bunch of new editing tools. To be fair, back in the days of the coverage, hardware wasn't powerful enough to support this feature-centric digitizing approach that requires on-the-fly calculation of coincident features or the geometric intersections. So today's computers are powerful enough to support this feature-centric digitizing, and ArcGIS supports this through a lot of tools they have, like the autocomplete polygon, split line tools, all of these that you'll see during some of our editing exercises. ArcGIS also supports topological editing of coincident boundaries or nodes through something called map topology. Map topology, you'll see, at during a demo that I'm going to do, and it is supported at the lowest license level of ArcGIS, at the basic license level. So it's a way to edit coincident features and move all coincident features at one time without having to move them individually. So a few more advantages. File size is really no longer an issue because hard drive space was much cheaper. A second often cited advantage of topological data structures is the smaller file size. So the topological data structure, like the coverage, people often said that they were smaller because they only stored features one time for shared polygons and where lines come together at nodes. However, theoretically, non-topological shapefiles that have coincident features, essentially more features stored, are rarely, if ever, double the size. That doesn't happen. So even though people said that the coverage would be smaller, the shapefile was by no means twice the size, just because it stored things twice. It didn't store everything twice, by the way, just coincident features. So with the shapefiles, even though they're not, topology is not stored with them, you are still able to find adjacent features and do some topological kind of actions through the software. For instance, and let's just do a quick demo here. Here's ArcMap, and I also have ArcCatalog here. And notice in my Topo demo folder here, I have a bunch of shape files. I've got a geodatabase too that I'm not going to work with right now, but I've got these shape files. And so I'm going to drag a couple of these shape files over to my ArcMap, and let's just do the municipalities here, and maybe the pump stations. All right. Okay. So these are two different shapefiles. What if I wanted to know how many pump stations were in the city of Asheville, which is this municipality? Well, I'm going to select the city of Asheville, and then I'm going to use select by location to determine how many pump stations. I'm going to select features from pump stations that intersect the selected feature in my municipalities layer. So this is a topological kind of function, really. It's determining the spatial relationship between these two different shapefiles. I'm looking to know how many pump stations are contained within that one selected polygon. So this information is not stored in the data structures. The features are compared on the fly in the RAM using the select by location tool in ArcMap. So you can actually get at some topological kind of relationships with shapefiles using the application ArcMap and the select by location within it. Things you cannot do are more advanced things like networking. So it allows you to get at some of the basic topological functions using select by location. Okay. I'll let you read this slide for more information on that. So, in the GIS, a line is an open sequence of points in which a first and a last points are called nodes, and the intermediate points are called vertices. The direction which you start and digitize a line, if you start here and work this way, gives the line direction. That's important to understand. Lines have direction based on the direction they were drawn. They can also have things like length. With the shapefile, the newer way of doing things, you could have multi-part lines that were connected or not connected. That was a big advantage. You could also have more complex polygons with the newer way of the shapefile. You could have overlapping polygons, you could have holes in polygons, you could have multi-part polygons. Back in the days of the ArcInfo coverage, topology was implemented or enforced in a very strict manner. You could not have overlapping polygons. You could not have multi-part polygons, and you could not have holes in polygons. So the newer data structure allows more flexibility with the way you model with your features. So there are two types of topology in ArcGIS. Map topology is a simple topology. It is imposed on simple features during an edit session. Map topologies can be created with any license of ArcGIS. So if you have a manhole on the end of a line, it's coincident with the end of a line, so a point and a line layer, and you want to move that manhole and you'd like the line just to move with it, if you created a map topology and that manhole and the end of the line are coincident, if I move the manhole, the line will move with it. So creating a map topology allows you to edit and manage coincident features as one unit rather than making two edits. That's a really useful way to manage topology during an edit session. Again, that's available at all license levels. Geodatabase topology is only available at one of the two higher license levels. The standard and advanced license levels of ArcGIS allow you to work with geodatabase topology. Geodatabase topology is implemented as feature behavior and rules. They allow a more flexible set of geometric relationships to be modeled than when topology was modeled in the old ArcInfo coverage as a data structure. So we're going to not talk a ton about map topology in this slide because we'll come back to it in a demo, and mainly because this is more of a geodatabase topology discussion. But a couple of terms to be familiar with when you work with topologies. The terms lines and arcs are referred to as edges because they can be shared, as well as the places where edges intersect, which we'd normally call points or sometimes vertices. They become referred to as nodes. We'll come back to map topology and we'll see it in an editing exercise and in a demo. So with map topology, remember the important things are that it's available at a basic license level. It only works during an edit session, and it just helps you maintain coincident features that are already coincidence, maintain that coincidence, and use them as a single and edit them as a single item. So when do you use map topology? You can use it on shapefiles. So it's something that's implemented at the application level through ArcGIS. It's not part of the data structure. If you've only got a basic license, and if you've got some coincident features, connected features that you need to model and keep connected. So how about geodatabase topology? With geodatabase topology, each feature in a geodatabase contains its own shape and can exist on its own. But the way we model geodatabase topology is that it's based on coincident geometry, and we store feature classes that have some kind of spatial relationship inside of a feature data set. So anytime you want to model geodatabase topology through a set of rules, your feature classes that are going to participate in the geodatabase topology need to be in a feature data set. Remember, feature classes in a feature data set must all have the same spatial reference. Within that feature data set, you can then define a set of rules that help you to model how real-world features are connected or related to each other spatially. So like a shapefile, the coincidence of features can be computed on the fly. The topology rules are checked through validation. This information is not stored in tables. The features are checked against a set of rules on the fly. So the power of this really becomes that you can check a lot of data for errors using this tool. So again, we were working with coincident geometries when we talk about topology in the geodatabase, just like coincidence is how features are managed in the shapefile and different from how it was done in the coverage. When we talk about topologies, edges are line segments that define lines or polygons, and nodes are the points at the end of an edge. Pseudonodes are a node connecting only two edges without a logical split defined by another line coming in. It could be something like a street block. Main Street has a block 100 and a block 200. So in these examples, polygons A and B have a shared edge of E, and that shared edge is coincident and stored twice in the database. The same with these two lines. Line A is defined by node C and E, and line B is also defined by that node E, but another node D. So this node here is stored in the database twice as part of the definition of this line and the part of the definition of this line. So with this system, very little information is written to the geodatabase. Topology in your feature dataset has properties that are stored in the geodatabase, and these topological relationships are determined and maintained on the fly. So you put your feature classes in a feature dataset, you define your topology, and you define the rules that go in it, and you evaluate your data or validate your data against that set of rules. You set up the rules you want, so you set up the topology. So in the geodatabase, there are over 30 rules, and they're organized by feature type that they apply to. Some rules apply to a single feature class. Something like you could put a parcel layer, a parcel feature class of polygons in a feature dataset, create a topology, and put a rule in that a parcel layer, the polygons in a parcel layer, must not have gaps. And so if the data was not edited and built in a way that kept the errors out, this would be a way to show you all of the gaps in a polygon feature class. Another example of a single feature class rule would be polygons must not overlap. You could apply that same rule for a parcel feature class to determine where parcels or polygons in a parcel layer overlap. So it allows you to find errors in your data. Other rules work between feature classes. Like you might have a points layer of manholes, and then you have a line layer of sewer lines. We know out there in the world that a sewer line connects to a manhole. And so in your GIS, how would you find any manholes that the person editing and building the data didn't do a good job and snap it to the end of a sewer line? Sometimes that distance is so small you can't see with the naked eye, so you could use a topology rule that would show you every manhole that's not connected to the end of a sewer line. If you wanted to model flow through a sewer network and a manhole is not connected to the sewer line, the network would not work. So when you create a geodatabase topology, you define properties in the geodatabase, things like the cluster tolerance, which tells you the distance between features before they're considered coincident, for them to be considered coincidence, which feature classes participate, relative ranks for each feature class, for what feature class moves to the other feature class, a set of rules. All of this is managed through ArcCatalog and created in a feature dataset. So the ArcCatalog topology wizard has 6 steps. You name the topology. You apply the cluster tolerance. The cluster tolerance is a very small number. It is typically, you take the default, really small, defined based on the precision of the data. Select your participating feature classes, set coordinate accuracy ranks, apply the rules, and validate the topology. So this is a wizard that shows some of the defining topology, your new topology, You set up some rules: must not overlap, must not have dangles, contains points. And then you set up, these are the rules that are being set up over here. And this is a few more than you see from the wizard here. You got to make sure to specify the cluster tolerance. Remember that ArcGIS calculates the minimum value as a default and that the units are the same as the feature data set. So errors smaller than the tolerance aren't reported. In this case, you can see the error is way out here in the 5th decimal place, and the coordinates for this are feet, so that's a very, very small number. Normally, we take the default cluster tolerance. From there, you define the feature classes that are going to participate in the topology. You can have multi-points, lines, and polygons, or you could just have a single feature class if you were looking at something like trying to find the gaps between polygons in a parcel layer. From there, you define ranks. This defines how vertices move during the validation. So if you validate topology, if any feature classes move based on the cluster tolerance, this will ensure the ones that are moved to match others. From there, you define the topology rules or add the rules. This is a tax parcel that must not have gaps. That is a single feature class rule. If you look at this one, its structures must be covered by another feature class. So the top 3 rules are within individual feature classes, and the bottom 2 are between feature classes. After that, you validate the area, or you validate the topology. So we work with dirty areas, validating errors and exceptions. So let's just run into these. So when you validate the topology, you when you first create a topology, everything is considered a dirty area or invalid, essentially. Dirty areas are areas that have not been validated against the topology rules. So once you validate your topology, you're able to start fixing errors in the topology rules. Dirty areas represent areas where spatial integrity of the topology has not been validated, vertices aren't snapped within the cluster tolerance, and rules have not been tested. Dirty areas may contain existing or undiscovered errors inside the topology, and they're allowed to persist in the database. So you can leave dirty areas in the database, but they're not, oftentimes you fix them. This is an area in the topology that's been changed and not yet validated. So this polygon, there was a gap here, and they've created a new polygon based on that gap, and since it hasn't been validated, it's a dirty area. So when you make an edit, the areas edited are dirty areas and need to be validated again. So what validate does, it snaps vertices together that are within the cluster tolerance. It accounts for ranks so that vertices are moved to the feature classes with the highest rank. So if you know one feature class is more accurate, you make everything snap to it. It adds vertices where features intersect if there isn't already a vertex. So you want to be careful when you start thinking about vertices moving. That's a scary kind of thing for a GIS person to think about. You don't have a lot of control over how they move. So you want to limit feature movement by using a really small cluster tolerance. Some people sometimes think, well, maybe I'll put in a decent sized cluster tolerance to really make all things fit together. You really don't want to do that. You want a very small cluster tolerance. If you need to move things to make them match better, that's more of a manual process. Rules are then verified with features. Violations of the rules are denoted as errors, and errors are stored as a property of the topology. Errors can also persist. You can mark errors as an exception, but you cannot delete errors. So sometimes, like a sometimes an error is an actual valid feature. An example would be sometimes we one of the topology rules is that lines cannot have dangles, and that means a line must always be connected to another line. And for a street network, that's a good rule to run to find out if any streets aren't connected properly. However, a road that's a dead-end road is a dangle. It's an error based on that rule. However, that error is acceptable, or it's an exception. So you can mark it as an exception. Alright, so dirty areas are created anytime feature geometry has been modified. You can validate the topology in ArcMap on dirty areas. It allows users to define their own workflow. And a topology essentially has one of three states. Either it's not been validated, it's been validated with errors, or it has been validated and there are no errors. Another thing about validating topologies, when you create a topology, it asks you right off the bat, do you want to validate the entire topology? You can also validate just in the current extent. So when you've edited an area, we often will just validate just a small area of the extent instead of validating an entire topology. It takes less time. So errors and exceptions. They occur where rules are violated in dirty areas during a validate topology. Errors are persisted and stored in the database, and they can be viewed in an error sheet or displayed. They can also be marked as exceptions. You cannot just delete errors. You can either leave the error in the database, fix the error, or mark it as an exception. So editing features in a topology, this is a shared line. It's actually coincident between these two polygons. It consists of features or parts that are coincident. They share the same space. So when you go to edit it, there's a topology edit tool. So just like there's an edit tool here, on the topology toolbar there's a topology edit tool. And it allows you to discover features that share geometry. Features that share geometry all become part of the edit. So with this tool, when you edit that, keep in mind this line, this fuchsia selected line, that's the color selected when you select coincident shared boundaries. There's two lines there. They're coincident. And so when you reshape it, it reshapes both of the lines. The area becomes dirty again, and it has to be revalidated. So the boundary between the two parcels has changed, but both coincident lines were edited. So to fix topological, the different topological editing tools you can work with, you have the fixed topology tool, the error inspector, validate selected dirty areas, portions of dirty areas, or the entire topology. You can also, with the topology tools, you can do things like construct polygons from lines. So if you have a set of closed lines and you want to construct polygons from them, you can do that with the construct features tool, and we'll see that when we bring in some closed polylines from CAD data that represent buildings on our campus. We'll generate polygons from those. You can also show shared features, and there's other tools as well. So as a summary, ArcGIS topology, the geodatabase topology, stores little information in the geodatabase. It stores a bunch of properties like participating feature classes, cluster tolerance, relative ranks and rules, dirty areas, errors and exceptions. Shared geometries are discovered on the fly during manipulation of the topology. It looks for coincident vertices between features on the fly in the memory of the computer. It can be done between features within a feature class or between features in different feature classes. There's advantages to the geodatabase topology. Number one, it works with today's computers and the processing speeds of today's computers in a way that that the old data structures didn't. It's better at modeling real-world features through a simple data model inside of your database management system. The data is stable. You define the topology through a set of rules. There's a greater range of integrity rules to apply, more flexibility, improved data integrity. It can be integrated with the multi-user environment, supports really large continuous data sets. There's a bunch of editing tools that go along with it. And that is your topology toolbar. This is your error inspector. You can right-click to zoom to errors, mark exceptions, and even apply fixes to some of them. So the final thing I want to mention is all these topology rules for geodatabase topology can be found through a topology rules poster that you'll see as part of ArcGIS desktop and in our Moodle class. I'll bring that up and show it to you as well. Let's just look at it here real quick right now. So how do you know what rules can be applied? In Moodle, under our course information, the topology rules poster is available here that shows you all of the rules, and you'll see this also linked in the virtual campus course. But these are some of the rules that we should be familiar with. So if you wanted to make sure your polygons didn't have any overlapping polygons within one feature class, you would use this one. Now when you're looking at the different rules, make sure to read this information about how to read these. But if you see one gray icon up here, this means it's a rule that works on a single feature class. This means it's a rule that works on two feature classes. This topology rule will return errors for, it says that features in the polygon feature class of your choice must contain a point from this other feature class. And so essentially any polygons that don't contain a point show up as an error. So we'll see some of these. Here's a must not have dangles. This is the one that we'll use as well. So any lines that are not connected show up as errors. Single feature class rule. So we will come back to some of these rules, and we'll see some in our in a demo that I'll do on geodatabase and map topology, and we'll also see it during our campus geodatabase project coming up in a couple of weeks.